Okay, we're starting. We are going to continue next time from last time, section 1.1. Finally going to finish it, move on to 1.2. Which we should get through relatively quickly. We'll see how quickly we get through that. So there's no quiz today because it's like a religious holiday with more than a handful of people missing. So I'll give you the quiz that I was supposed to give you today on Wednesday, so that everyone gets a chance. And so without further ado, let's move on. So again, I'm going to continue throwing a lot of material your way, so just buckle in, sit tight. Today we're going to talk about increasing and decreasing functions. So this is going to be very important to us later, so let's just talk about the concept of what this means when a function is increasing. So the function f of x is increasing if f of x2 is greater than f of x1 whenever x2 is greater than x1, i.e. the function goes up as you move from left to right. This behavior is called increasing. Where a function is doing that, it's going to be very important for us to know when a function is increasing or not. The idea is the function is doing something like this. So if you have two x values, x1 and x2, where x2 is bigger than x1, which is what I'm saying here, then the y value here will always be bigger than the y value for a smaller x value. So this is f of x1, that's f of x2. Notice that whenever this x value is bigger than that x value, the corresponding y value for this will be bigger than the corresponding y value for that. This means your function is moving up as you go from left to right, and this is called increasing. Similarly, there's a definition for decreasing. The obvious definition based on that one. If f of x2 is less than f of x1 when x2 is greater than x1, i.e. the function goes down as you move from left to right. So the illustration there would be something like this. So this here, x2 is bigger than x1. The x2 value is actually smaller than the f of x1 value. So this means the function is going down as you move from left to right, and that is called decreasing. Now there was one point where I told you guys that we could have used calculus to find the vertex. Notice that the vertex for that first problem that we did, the word problem with the hot dog stand, the vertex was the maximum point. Notice that one way we can think of maximum points is any point where you're increasing on the left, decreasing on the right. Keep that in mind. We'll actually return to that idea later on. Right? So if a function is doing this, and then after some point it starts doing that, you can say, oh, here it reached the biggest it could possibly be in this region. So that's why increase and decrease are going to be important. We're going to come up with formulas that will tell us when this happens without even knowing what the graph looks like. So that's going to be nice. But it's an important idea. Note a function can be depending on the interval consideration. So not all functions will exhibit what is called monotonic behavior, meaning it keeps doing the same thing. Sometimes a function can, of course, switch on you. A very familiar function that does this, for example, is y equals x squared. So if I were to ask you another important thing that we're going to be talking about later, what is the interval of increase for this function? Right? Which I might abbreviate INC. And what is the interval of decrease for this function, which I might call DEC? Right? So can you tell me an interval where this function is increasing versus decreasing? Yeah.
From 0 to infinity, it's increasing. And negative infinity to 0 is decreasing.
Right, so we see that from this point on, it's moving up as I go from left to right. So basically it's increasing on that interval from 0 onwards. Similarly, from negative infinity to 0, it's moving down as I go from left to right. Therefore, it's decreasing on that interval. At 0, notice I did not include 0, because at 0, it's kind of flat. That's where it changes from one to the other. Right? Points like that we'll be able to locate with calculus. So of course, it's a quadratic. We could use the vertex to locate points like that. But in general, there is no formula to locate a point like that. With calculus, we will be able to. These points are very important. Max, this is what's called a minimum point. So we have another function. This. Let's say this is 4. This is 2. This is 0. This is 1. This is 2. This is 4. So this is probably some sort of cubic, maybe a little larger. And so here, what is the interval of increase, interval of decrease?
Are you asking for x equals y?
Oh, intervals, they're always referring to the domain set, so it's always going to be the set of x values. Yeah?
Negative infinity.
Where is it increasing?
Negative.
Infinity to negative 2.
Negative infinity to negative 2.
And from 2 to infinity.
Right, so in this region here, I'm moving up as I go from left to right. That behavior stops right here, so it stops from at negative 2, so it goes from negative 3 up to negative 2. To say that it goes for several intervals, you put that union symbol, so similar to what we're doing to the domain. And notice that that behavior happens from 2 to infinity. We're going up as we move from left to right. So 2 to infinity is the other one. And decreasing? Negative 2 to 2. So between here, notice that I'm going down as I move from left to right. So we're decreasing that region. That happens between negative 2 and 2. Someone else? Any questions so far? So that's increasing versus decreasing. And we're finally done with 1.1. Moving on to 1.2. This section we're going to talk about combining and transforming functions. Three main ideas here that I wanted to remind you of. Supposedly you're all familiar with it. One is the composition of functions, function composition. The other is the transforming of functions. Which we're not going to appeal to directly, but it might come in handy when we're doing graphing and things of that nature. And actually, function operations. Basically, this just means we can operate on functions similar to how we operate on numbers. We can add them, subtract them, multiply them, divide them, that sort of thing. And that refers to function operation. So with these guys, we can create new functions, given that we already have some old functions. So it gives us a mechanism to create new functions, and they might be convenient for whatever reason. For example, you'll notice that in the very first word problem I gave you, the hot dog stand problem, when I had to figure out revenue, I actually multiplied two functions. I was taking advantage of the third I gave, where I multiplied the price by the number of items sold, which was itself a function I had to figure out. And composition of functions, the difference quotient is an example of that, right, where you have to take that f of x plus h part. And transformations is just about, once you know on the graph, how you can shift it to get new graphs. Right, so let's go one first, talk about composition. Basically, this refers to is plugging one function into another. Function of functions is called decomposition of functions. Or you can refer to them as composite functions. When we get to derivatives, we're going to learn a rule called the chain rule, and it's for actually differentiating composite functions. So you need to know what these guys are and what they look like. Let's talk about notation. Let f of x, g of x, two functions. Let's say domain of f, domain of g. Codomain of f, codomain of g. How do I want to set this up? Maybe f of g, so let g be first. So say g is a function whose domain set is A. A can represent any set that we want, like the set of real numbers or the set of positive numbers or whatever. And the codomain is the set of outputs where I pick my outputs that I call set B. Then pretend that the codomain of G is actually the domain of F, and then F will output things in the set C. So what we have here is a group of elements A, B, and C. Now what's going to happen is G is going to take things from A to B. So your G function is going to start here and output things there. That's what the function G will do. F will take things from the set B and assign them to things in the set C. Now the composite function, there exists a function in this case that will go straight from here all the way to here, right? You sort of cut out the middleman. So instead of having two functions, you can have one function that goes from the end point, the first point, to the very last point. And I'm just illustrating here with three sets. This could actually go on for a long time, right? You can have like a string of 100 functions and then figure out one function that goes all the way from the beginning all the way to the end. It can greatly simplify computations. And so that kind of function is very useful to have, and it shows up all the time. This function would be called f of g. So let me introduce that notation. F of g of x is decomposition of f with g. That's what I call it. It's called f of g. Right, so if you hear me refer to f of g, I'm talking about this guy. And basically its definition is the following. Basically, you're taking the function g and you're plugging it into the function f. You plug one function into the other. That's what we're talking about. So g does something, I take that output and I plug it in as an input for the function f, and I say I've created the function f of g. Right? And basically this is a function that cuts out the middleman, gives you one simple definition to jump all the middle intermediate steps. So it's a very important kind of function composition. So let's do some examples. So they actually write down example. Nothing too bad here. X squared plus 1, 2x plus 4. Here, find f of g. G of f. F of f. G of g. Let's go with f of f of f. That should get us back in the group. So this is called function composition. F compose of g, or f of g, just means you take the function g, plug it into the function f. Okay. In this case, for these two functions, what would f of g look like? Where the x is, typically. Right, so f of g means f of g. So it means every see an x in the f function, you're going to replace the g function. So basically you're going to have g squared plus 1. And we know what g is. G is 2x plus 4. So then I would have 4x squared plus 16x plus 16 plus 1. That's 2x plus 4. So it's 4x squared plus 16x plus 17. Right? What about g of f? This way, say g, you plug f into g. Now g is the function that says you're going to take 2 times the input plus 4. So I need 2 times the input plus 4. The input in this case is x squared plus 1. So I'm going to multiply that by 2 and then add 4. So this is 2x squared plus 2 plus 4. 2x squared plus 6. What would f of f look like? So I'm going to take this function and I'm going to plug it into that x. So you can compose a function with itself. It's actually no problem. So I'm going to take f and I'm going to plug it into itself, f. Now f says I'm going to take the input, square it, and then add 1, which is the definition. Now f says I take the input, square it, add 1. And this I can simplify. This is x to the 4th plus 2x squared plus 1 plus 1. And that's the answer there. Gawk. G, you plug G into G. G says we took 2 times the input and then we added 4. You don't really have to write these 2 lines, you can just jump straight to here. I just want to emphasize what's going on. So this would be 4x plus 8 plus 4, 4x plus 12. We get that one. Like I said, compositions can actually go on for a while once it's useful. So in this last example, we do 3 of them. F of F of F. So you just take F, you plug in F, you plug it in F. Now F says what? You're going to take the input, you're going to square it, and then you're going to add 1. But the input in this case is F of F. Now F says you take the input, you square it, you add 1. And F itself says you take the input, you square it, you add 1. So that's what that function would look like. And again, we can simplify if we felt like it. Questions on compositions? Are we all familiar with this idea?
Can we leave it like that? Like,
Yeah, unless I ask you to simplify. Any questions on this? Plug-in functions into other functions? Because notice when you take, earlier when we had things like the difference quotient, I would say like f of x was, I don't know, x squared minus 2x plus 5. And then I asked you to compute the difference quotient f of x plus h minus f of x over h. Notice that you could think of this guy as a composite function, right? I could think of it as g was x plus h, and I'm plugging this into the f. Right? So it's actually computed the composite function. Remember last time the mistake that was pointed out was you can't just write this down and add an h at the end. It's not the same thing. Your x plus h must replace each x value. Another idea we want to talk about here, I think, would be decomposing functions. When we get to the chain rule and derivatives in chapter 3, the things where we use the chain rule, you're going to sort of want to decompose things in f of g, which is f of g of x. We can think of g as the inside function. And f as the outside function. And basically decomposing a function is when I give you something like this and you can decompose it into an outside function and an inside function. In some convenient way. It's not a unique. It's not a unique way to do this, but there's a more obvious way. So example, let's say I gave you a function h of x, and it looks like and I ask you to decompose that. into two functions, where one you can think of as an inside function and the other one you can think of as an outside function. Or decompose that. Okay, so let's keep this notation where I'm thinking of G as the inside and F as the outside. So in this case, what would F of X be? What would G of X be?
F of X, 3x to the third plus 7.
And G would be?
4x squared minus 1.
So now there's no unique way to do this. I could have cheated and said F is this and then G of X is just X. Would also be a correct idea, a correct answer. But you want to sort of do it in the more obvious way. Here you can see that there's something taking place inside of brackets, right? That kind of gives you the idea that something's being plugged in this position, right? So you can think of this as a function being plugged into 3x cubed plus 7. And I'm taking the function 4x squared minus 1 and plugging it into that function, right? So I think of this inside the brackets as the inside function, and I'm going to take this and plug into here, and that gives me the outside function, right? So pretty much wherever is brackets, I just call that thing x, and then take that thing that was inside, that's my g. What would be the example here? Sometimes it's probably easier to identify who's the inside function first and then work backwards to the outside. So who's the inside function here?
G is 4 minus X.
You think of 4 minus x squared, because he's the guy that's inside of something. He's inside of a cube root, right? So what would the f be?
Q
Plus 7.
What?
Cube of x plus 7.
Cube root of x plus 7. Right? What about this one?
G of X is X squared plus 1. 3 over cube of X.
Well, radical x.
Radical X,
Yeah. So when we get to chapter 3, I'm going to give you a rule that talks about inside functions and outside functions, and I'm going to say something like the derivative of a composite is the derivative of the outside function times the derivative of the inside function. And basically, this is what you're going to have to think in your head. Right? You're going to have to be able to identify which function is being plugged into what, and that's going to determine what the rule is. As well as knowing that you have to use that rule, it's not something I'm going to tell you. I'm not going to say, hey, use the rule, right? I'm just going to say, blah, differentiate that. And you have to know, oh, I have to use that rule that deals with inside functions and outside functions, and this is my inside and that's my outside, and it's going to tell you how to fit the pieces together. So that's coming in chapter 3, but for now, you just need to be able to practice seeing this. So we have to come here. We're probably 2 or 3 weeks away from that, but hey, start early. Transformations. So I've been quizzing you on some basic graphs. I asked you how to graph x squared, how to graph 2 to the x, how to graph lnx, and all these things. But now you can actually make graphs more complicated because you can shift them and it can change not only the picture, but the formula will change. And so there are a bunch of rules that describe how formulas change. Transformations refer to affecting a graph by stretching, shrinking, rotating, or reflecting, right? So those are some transformations. And so the basic ones are the following. Given f of x with its graph describe how the following will change the graph of the function. So first we can talk about reflections. So if I'm given the graph of f of x, now what if I ask you to tell me what does f of minus x do? If I replace all x's with the negative in the function, what would happen?
Negative the y.
Reflect in the y-axis, right? So, for example, if I have y equals x cubed, which looks like that, then if I have y equals minus x cubed, it flips in the vertical axis, and the graph will now look like that. Right? That's called a reflection in the y-axis. So replacing all x's with negatives actually flips it in the y-axis. What if I did a negative on the outside of this graph?
The x-axis.
That reflects in the x-axis. I can do the same example here. So if I had y equals x cubed, it looks like this. Or maybe x squared would be nicer, just to be different. So I have y equals x squared, would look like this. And if I put a negative on the outside, minus x squared, it actually flips in the x-axis and looks like that. So once you know how to draw the graph of this, you'll automatically know how to draw the graph of that. You don't have to plot points and make a table anymore, because you can just shift things. So those are reflections. Those are certain transformations of graphs. Let's talk about stretching. So what if I said C f of x, where C is greater than 1, what does that mean? How? Stretch vertically by how much?
By C.
By a factor of C. So if I had a graph and before it went up to 1, and that was y equals f of x. Then if I have y equals 2 f of x, I multiply that whole function by 2. Now it's going to stretch to 2, right? Because I multiply the 1 by the 2. Maybe I should put a different number here. If this was a 3, then this would be a 6. It doesn't just stretch, it stretches by a multiple of 3, by a multiple of 2, right? Because they multiplied all the y values by 2, so the 3 will become 6. That does a stretch vertically. And similarly, if I did 1 over c, this actually shrinks vertically. Graph. And this is 4. And this is y equals f of x. And over here I have a graph y equals 1/2 f of x. So now it was at 4, but now it's going to go to 2. Because it's going to shrink everything vertically. All my y values are going to be multiplied by 1/2. So it shrinks it vertically by a factor of 2 in this case. But if I had f of cx, where c is greater than 1, what does that do? graph. This was a 1 and a 5. This is y equals f of x. So if I do y equals f of 2x, how would that graph relate to the original?
2 times f of
You stretching horizontally.
Nope. On the inside, it actually goes the opposite. It's kind of weird. Because what happens is, if I multiply by 2, it means my x has to be half the original value to make the same corresponding y value. So when you're operating on the inside, things work kind of the opposite way of what you would think. Doubling actually means halving, right? So this thing will actually get smaller. This actually shrinks horizontally. The opposite is true. So if I have 1 over c times x, this stretches horizontally. And another thing to notice that when I'm doing something on the outside of my function, it's actually affecting the y value. Things happen vertically. Whereas when I'm doing something inside the parentheses and affecting the x, things happen horizontally. So that you should also note. And when you're affecting the horizontal, things actually go the opposite way of which you think. So what you would think would be a stretch would be a shrink, and so on and so forth. Let's actually talk about shifting. So let's say I have f of x plus c, where c is greater than 0. This would shift c units up. And so that's like y equals x squared. It would look like this. Whereas y equals x squared plus 4 would look like this. It's the same graph, it's just shifted up 4 units. Where f of x minus c, that's just shift down. So I'm doing something on the outside of f, so it's very intuitive. You add a number, it increases. You subtract a number, it decreases. On the inside, it goes the opposite way. So if you have f of x minus c, again, if c is greater than 0, this actually shifts c units right or left.
To the right.
Right. So subtraction, intuitively, you might think it's going to the left, but it goes the opposite. It actually goes to the right. To the right. So if I have y equals x squared, I have this. If I have y equals x minus 1 all squared, I'll have that. Right? It shifts 1 unit to the right. F of x plus c shifts c units left. I think that's it. Well, ideas like that will come in handy when we're back to graphing. For any other problem where we'll actually need graphing. 3. Operations on functions or function operations. not really going to give an example of this. It's kind of normal. So this is like if I'm taking f plus g of x, I can add two functions together, and I just add like terms, basically. And so I can do a plus or minus, and I add or subtract the functions. Fg of x. Notice that there's no circle in the middle. That just means simply multiply the functions. I can have f slash g of x. This means divide the functions. And notice that works where g of x is non-zero. You can't divide by 0. So that's just functions operations. So these might come in handy sometimes. So for example, with the subtraction, if I'm computing profit, notice that profit would be revenue minus cost. So you actually do a function operation to figure out that function. And it's pretty intuitive. You just subtract the two functions and you you subtract like terms. That's 1.2. Wasn't much to cover, just some basic concepts that we wanted to go over. The most important part is composing and decomposing functions and recognizing when one function can be decomposed into an outside and an inside. I had notes here about the domain, but I don't think I want to talk about those. Let's actually jump to 1.2. Linear models. Now we're going to remind ourselves about the equations of lines and how we use them to solve word problems. And what kind of word problems can be solved with the equations of lines. A linear function is one that can be written in the form y equals mx plus b. Its graph is a straight line. That form is a very common form to have, write a linear equation in, and so it actually has a name. The above form is called the slope-intercept form. Notice here that m is the slope of this line for the equation of a line. M is the slope of the line. B is the y-intercept of the line. That's basically the point where it touches the y-axis. You all know everything I'm going to say in this section. Just want to make sure we're all on the same page for those of us who have not been in school for a long, long time. Right. So y equals mx plus b. Anytime you see this, this is the equation of a line. M, I should probably mention, m and b are constants. say that because now I remember some mistakes that I saw in my class last semester. Where they were finding an equation of a line, and they wrote m had some x's in it. It was like something radical x, and then they multiplied this x, and they told me that was the equation of a line. It's not the equation of a line. You can't have a radical x in it, right? It has to be a constant times x plus a constant. Okay. So m and b are constants. If they're not constants, it's not a line. Okay. Now let's talk about the slope. It's a very important concept. Slope is so super important. You'll see why it's so super important in chapter 2. But slope is a very important concept. So the slope is a measure of steepness. And we're going to talk about another way to think about slope at the end of this section. We'll actually get to that today. Yeah, we definitely have time to get to that today. By definition, how we measure steepness is describing how far we move to as a ratio of how high we go. By definition, m equals rise over run. So it's a measure of the steepness of a line, right? So if your line is passing through 2 points, you're going to measure how high up you move after how far you've gone horizontally. This is called the run. This is called the rise. So it's a measure of how steep something is. So if something is positive, has positive slope, the bigger the number, the steeper the line. So if a line passes through, let's say we know a line passes through 2 points, x1, y1, and x2, y2. Then m equals altogether y2 minus y1 over x2 minus x1. You'll be able to say that in your sleep at this point. So here's your line. This is the coordinate where you have x1, y1, x2, y2. So now if you're measuring how far you move from this point, here, it's just the difference in the y values. That's y2 minus y1. That ends up being the rise. And if you're measuring how far you travel here, that's x2 minus x1. That ends up being the run. And then you just divide this by that. That gives you the slope formula. Very important formula. Once you know 2 points that a line passes through, that's the formula you're going to use to find the slope. If you guys mess up on equations of the line in this class, you're going to be in so much trouble. Just did it in algebra, did it in pre-calc, and I'm doing it again in calculus. What else do you want to say? Set x2, y2 equals xy. An arbitrary point on the line. So I have a similar picture, x1, but here my x2 I call it x, my y2 I call it y, because I just want this point to be x comma y. It can be any point that I'm shifting along this line. And so what we can do is we would get m is equal to y minus y1 over x minus x1, which I can actually solve to get y minus y1 equals m x minus x1. That's also an important formula. This is called the point slope form for the equation of a line. Point slope form. So this is it's very useful when you have a point and the slope. Useful when you know the slope. There are going to be tons of problems where I'm going to ask you to do this. I'm going to be asking you when we get to chapter 2. Find the equation of a tangent line. A tangent line is just a straight line, and at some point you're going to be able to figure out a point and the slope of the line. You're just going to use this formula to find the equation of the line. Just because I call it a tangent line shouldn't matter. It's still just a straight line, so all the rules to straight lines will apply. So you need to remember how to do all that stuff. Another form, ax plus by equals c. This is called the standard form for the equation of a line. We won't use it very often, but I guess for the sake of completeness, I'll just mention it. AB naught goes to 0. By some definitions, they have to be integers, but you can have lines where they don't have to be integers. It's called the standard form for the equation of a line. Hopefully I haven't said anything weird so far. Of course, because I'm taking the time to go through all this, you guys have no excuse for not knowing this at this point. Let's look at things differently now. Did I do everything else I wanted to talk about? So these are very abstract numbers. Let's actually put some meaning to things. Let's look at slope in a different kind of way. Which you may or may not have done in algebra, more than likely not, but you may have done it. But I'm going to want to emphasize it because it's going to be a very, very important concept in calculus of a way that we think of slope. So in a calculus class, this is how you're going to want to think of slope, basically. You're going to want to think of it a lot more generally than just a measure of the steepness of a line. It actually means something. Let me illustrate with an example. Now this object could be a car or Superman or whatever. It's moving at a constant speed. And in 2 hours, it covers 80 miles. Find the function f. That measures distance traveled over x hours. So this is my function f. X is going to be my input, and I'm considering it to be time in this case. It's going to be A, B. Find the slope of f, because as you'll discover, it will end up being a straight line. C, finally, I want you to interpret the slope in this context. Not just the number y2. No, tell me what it would mean. It's y2, so no, I want an English expression that would describe it. Okay, so if we're going about trying to figure out what this thing would look like, what do you think it would look like? How would we try to figure that out? So here's my function f, and f is measuring the distance that this thing is traveling. And x is this guy, where x is actually representing the time in hours. What would this function look like? Let's say I start timing this thing. There is some point, I'm measuring 2 hours, there has to be a starting point where I started the stopwatch, right? So let's say I started the stopwatch at position 0. This thing is just zooming by and I started the stopwatch when it passes a certain point, which I call position 0. So at position 0, the distance it's covered is 0, so my object is going to be here, right? Now, when x is 0, my position is 0. When x is, what's the other point that I know about? When x is 2, what is the position? 80. So it goes from this point to that point over 2 hours. Now it's traveling at a constant speed, so you expect it not to go up or down, it's just going to go straight, right? As it moves, it will cover a certain height. And it keeps moving, but it will cover an equivalent height as it keeps moving. All right, so every time I move a unit here, it will correspondingly move a unit here. The same unit will correspond to the same amount of increase. So I'll end up with a straight line. What would this function look like? F of x equals
2x plus 80.
Well, how would you find it? It's a straight line, so what are we going to do? We know what it should look like, right? So I know it should look like f of x should be y equals mx plus b. So the first thing we have to do is find the m. What is the m? Right? M is the slope. What is the slope here? 40. It's rise over run. So I've risen from 0 to 80, that's my rise, over the run, which would be the horizontal distance I moved, which is 2, so that's actually 40. My y-intercept, the b, would be 0. So this basically is my function. F of x equals 40x. Now this will describe the distance that this particle has moved, right? So after every hour, it's moved 40 times x in distance, right? So after 2 hours, you'll notice it's 80. After 1 hour, it would have moved 40, right, miles. So that was A. B, we already found the slope is 40. C, interpret that number. What would the number 40 be in this case? How do you interpret that number? What does that 40 mean? Yeah, well, we know it's the slope. Interpret it. What does it mean? Huh?
Distance travel.
Speed. The slope is the speed. It's the rate of change. It's how fast the thing. It's how fast the thing is going, right? It's how fast y is changing in relation to x. How do I even know its speed? Many ways to see this. One way to see this, which is probably going to be the obvious way, is to just look at the units, right? When I'm finding m, and I'm doing that y2 minus y1 over x2 minus x1, notice that what are my y values? My y values are on the y-axis, and my y-axis this time is being interpreted as distance, which is measured in miles. So my y2 is going to be 80 miles minus 0 miles for y1 over 2 hours minus 0 hours for this guy. So when I get this answer 40, it's not just a random 40, it's 40 miles per hour, which we all know is a unit of speed, right? It's how distance changes over time, right? So the slope, this 40 is not just some arbitrary number. In this context, I can actually think of it as how fast this object is moving. The slope tells me how fast y is changing with respect to x. Of course, there's a difference between slope, speed, and velocity, and we're not going to get into that too much. Speed is the magnitude of velocity in different direction. Whatever, forget all that technical physics stuff. The overall idea here is the speed or velocity of the object is what the slope is measuring. We can actually generalize this concept. That idea should hold no matter what my units actually are. So we can actually generalize that. The slope of a straight line tells us how fast the y, or it doesn't have to be y technically, the dependent variable changes in relation to the x, or the independent variable. So it didn't have to be, so in this case, we had miles per hour. But the truth is, that's just because that's the interpretation I gave it in this case. I talked about an object moving this miles and that many hours. But this could have been anything. It could have been the profits over the year, or the size of a brain tumor over several months, or it could be whatever. I can put any two units on this thing that I'm tracking with a function, right? And the slope would be interpreted as how fast this thing is moving in relation to that thing, right? So that's a very, very important idea. Slope isn't just it's not just rise over run. You can actually think of it as measuring a speed of how fast it is moving. I think this example sort of makes it obvious because the units are familiar units of speed. But that's, from now on, that's kind of how we're going to want to think of slope in calculus. Slope is a measure of rate of change, how fast something is moving. And if you remember what I talked about on the second lecture, where I was talking about what the purpose of calculus is, I told you half of it is measuring how fast things are going. It turns out, ever since algebra, when we talked about the straight line, we've already had a tool for measuring how fast something was going. It turns out to be the slope of a straight line. And we're going to actually use that idea to develop that concept a lot more generally. And that's going to give rise to what we call the derivative. But for now, I'm just going to let that sink in. We'll actually take advantage of that very idea in chapter 2. This is what chapter 2 is all going to be about. How the slope tells us about speed, or how fast something is moving. So let's look at some models. Examples. So a model is basically a mathematical abstraction of a situation happening in real life. Okay. So one example we've actually had before, there was the hot dog stand example from lecture 2. We actually used a straight line to measure how many hot dogs I'm selling every day or something like that. Hot dog stand example. Two. Let's actually give another example. Let's look at the example of a car rental company that has the following price structure. They charge you a flat fee to rent a car. So you want to rent a car from them, you have to pay a $50 flat fee, and then they're going to charge you $2 for every mile driven. So they're charging you based on the mileage after this flat fee. A. Find a function for C, the cost of renting a car and driving X miles. Interpret the slope of this function. Right? Meaning in English, tell me what it is, as opposed as just like in the previous example where slope means speed of the object. C. So I want to rent from this car company for a 200-mile trip, driving 100 miles away and 100 miles back. How much would that actually cost me? D. How far could I get for $300? Yep.
Would it be something like 50 plus 2 times X?
So C is equal to 50 plus 2 times X. So the 50 here represents the flat fee, right? So you're going to pay $50 no matter what, even if you don't drive the car. I want to rent your car, but I'm going to keep it in the lot. You just have to pay $50 right off the bat. This says I paid $2 for every mile driven. Right? So X miles cost $2X. So that part of the cost comes from being charged for every mile, per mile. So that's actually part A, that would be your function. Notice that it is a straight line, mx plus b. So part B, what is the slope here? Slope equals 2. What is the interpretation of the slope? It's how much you are charged for every mile you drive. Okay, so now math is getting real. That 2 is not just a 2, that's money out of my pocket right now. Now I really care. Right? Every time I drive a mile, ching, that's $2. So that would be a function that measures the cost of driving X miles. The slope would be 2. The interpretation is that's how much you're charged for every mile you drive. Of course, after the flat fee. because that's how you're going to want to interpret it. C. How'd you get that?
You substitute 200 into x.
Okay. So remember that C is cost. Here, X represent the miles. So here what we have is X is 200. We want C. Right? So, yeah. So you're going to go into this function that you already set up in part 8. You're going to plug in 200 for X. You're going to solve for C. So C would be 50 plus 2 times 200. That's 50 plus 400. That's $450. So that's how much it will cost me to drive 200 miles. That's an example. D. How far can I get for $300? What? 125 miles? Well, let's see. So in this case, I'm told the cost, right? So I know that C is equal to 300, and what I want is how far, which is a measure of distance. So X is what I want to find. Here, before I was told the miles, and I wanted to find the cost. So it's important that you can read and interpret. The problem is simple here, but I want you to practice reading very carefully. So notice that what we were given was money, which is cost, and we're asked how far, which is distance, which in this case is miles. Okay. So the distance is what we want to figure out. C is the cost, and I have a function. So what I'm going to do is I'm going to replace C with 300 equals 50 plus 2x. How do I solve that? First you subtract 50. Solving for x means you want to isolate the x on one side by itself, which means you need to get rid of everything else. You start by getting rid of things that are separate from x. Things that are separate from x are defined as things that are separated from it by a plus or a minus sign. The 50 is separate. You move it over by doing the opposite operation. It's adding over here, so you have to subtract it over there. So you get 250 by subtracting 50 from both sides. Now, you want to get rid of that 2. 2 is multiplying the x, so you have to do the opposite operation of dividing by 2. So you take 250 and you divide both sides by 2, and you get 1. So you can drive 125 miles for $300. Assuming a car rental company had this structure, had this pricing structure, you could figure out how far you could go for a certain amount of money, you could figure out how far a certain amount of money could take you, and it all came from you setting up a linear equation and figuring out what the slope means, and you can solve the problem. So let's actually deal with something here, because we're not only going to deal with linear equations in this class, so let's actually see why they're different. How would you know to set up a linear equation? So, 1. Easiest way to know if you have to use a linear equation, you're told to. Right? So remember in my hot dog example, I actually told you these things share a linear relationship. Right? So I can either tell you that things have a linear relationship. So that's a key word that you should look out for. I can tell you that it has a straight line. I could mention the word linear. I could mention the word proportional. Which proportional sort of means that it's a straight line that passes through the origin. So I can mention linear relationship, or it's a straight line graph, or it's linear, or use the equation of a line. I could actually get to say that. Use the equation of a line. So that's one way to know that you have to use the equation of a line somehow, is if they tell you that you're supposed to use the equation of a line. But notice in this problem, I didn't tell you had to use the equation of a line. You sort of just tried to figure out how to make that function, and it turned out to be a line. So how would you know if that was the right thing to do, or maybe it should have been a quadratic or something else? 2. You know you have to use the equation of a straight line or a linear model if the quantity you're considering is changing by a fixed absolute amount per unit interval. Usually time or distance is a very common example that we'll use in this class. And of course the interval here refers to the input values or domain. Right, so per unit input value. So it's, in this case, our domain was the distance, which was miles, so per unit mile, per mile is what you were talking about. But things are changing by a fixed absolute amount. So notice here, the cost that we had was actually changing by a fixed amount, $2 for every mile, right? Every mile you add on, it increases by $2. It's always going to be increasing by $2, exactly $2. It's not like, oh, the first mile is $2, then the next mile I'm going to charge you $5, then the next mile I'm going to charge you something else. No, I'm always charging you $2 for every single mile. You're always being changed by a fixed absolute amount, right? When any time anything changes in that way, it will change according to a straight line. The function that will model it will be a form y equals mx plus b. Right? And so everything that you know about y equals mx plus b, which I went over, how to find the slope, the y-intercept, all that stuff, will apply to this function. So those are two ways. So either I'm going to tell you, but even if I don't tell you, you just by reading the problem realize, oh, it's the same thing that's changing by the same amount every unit time or every unit distance, you know it's going to be a straight line. So that's when to use a linear model. Questions? Don't worry, don't look so bored. It'll get harder. I know you guys want to, I just want to make sure we're all kind of on the same page before I start making things interesting. We have about 10 minutes. Let's see where we can get. That's actually section 1.3. Move on to 1.4. 1.5. We actually skipped 1.4. So we deal with another very important kind of model, the exponential model. Now remember, a model is just a mathematical abstraction of a real world situation. Basically using a formula to describe something happening in real life. So linear models means that you can describe the thing that you're looking at by a linear function. So an exponential model similarly means you can describe the thing you're looking at with an exponential function. So this just means models that use exponential functions. How to know when to use them. So remember, just like how with linear models, there's a specific reason why I would know I would set something up as a linear function. So when things are changed by a fixed absolute amount, I'm always adding $2. So I'm always moving 10 miles, or I'm always doing the same constant amount of things. An exponential model arises if a quantity is changing. How would a quantity change for an exponential function? Do you remember? By a fixed. That's right, percentage. Percentage or relative amount. Right? So it's not a fixed absolute amount, which is just the same size of quantity that you're adding. When things change by a percentage, that's when you get what's called exponential growth or decay, and you need an exponential model to do that. So it's not that it's always changing by 2. You can say it's changing by 10% of whatever was there before, right? Now, whenever you look at something like that, that gives rise to an exponential model. When you say every time it grows by 10%, right? So at first, you might have $100, and I'm saying it's growing by 10%, right? Every month means after month 1, you take 10% of 100, you get 10, you add it. So after month 1, you now have 110, right? But then after month 2, you're not going to add $10 anymore, because you're going to take 10% of 110, which is $11, and you're going to add that. So now in the third, after the end of the second month, you're going to have $121, right? So you're not always adding the same thing. You're adding a percentage of what was there before. And if you add a fixed percentage per unit interval, that gives rise to an exponential model. Examples where these are used. So something like population models. Populations grow exponentially, right? They don't grow by a fixed number, right? You don't have a population that every year it increases by 10 people. That doesn't happen, right? Because the more people there are, the more babies they make, right? So the more people there are, the more it's going to increase. The more they are, the faster it will increase, right? Because now eventually those babies grow up and they start having babies, so you have more people having babies, right? So a population will often increase exponentially, at least in a certain period of time. For those of you doing 209, you'll look at a lot of more detailed population models that are a lot more realistic. Because populations don't just increase exponentially forever. That would be disastrous. So population models is an example. Radioactive, and population would include things like, not just people, but things like bacteria as well, which we'll have examples of this, people, bacteria. Pretty much any living organism will exhibit exponential growth. Cell division, when your cells start splitting, that represents exponential growth. Another thing, radioactive substances. It's another example. So if I take a huge mass of uranium or something, it will eventually decay radioactively, or carbon or whatever. Entropy takes place and things start decaying it tends to decay by a percentage amount of what it was before. Another example would be something like financial model would follow this. So how your bank account grows when it's in a savings account would be an example of exponential growth, or very slow exponential growth, because you're giving like 0.1% per year. Credit card debt grows exponentially. So it's not like a straight line. Your interest is charged by whatever your balance is. And so that leads to exponential growth. That's why something like credit card debt is so dangerous. Exponential growth is like crazy. We'll talk a lot more about this later. It can get really fast. It grows really fast, really quickly. It can get out of hand really quickly. So these are usually the models that we'll use in this class. I don't know anything else. No, I think that's the only examples I have. But in this class, these are some of the examples we're going to talk about, which are, it covers a wide range of things. I guess we'll stop there. So I didn't tell you what exponential functions look like. I'll describe that next time, talk about their graphs and things like that. Examples we'll save for after we do calculus. So we will actually come back to exponential functions. And yeah, so until next time, we'll stop there. So we'll have our quiz that I should have given you today next time. We'll pick up talking about exponential functions. Still, we're technically in our review phase. And hopefully we'll get to chapter 2 soon and things can start getting interesting. See you guys on Wednesday.